and half of them belongs to this cell. And how many of them? 6. There are 6 of those. 6. So it's 1 plus 3, and it's 4. Okay, there are 4 atoms in this unit cell. And we just discussed that one atom contributes 1 free electron. So that means there are 4 free electrons in this unit cell. Then if you want to get the density n number, then we will use this 4 electron and then divided by the volume of this cell. And then we will get the electron density n, because in this volume you have 4 electrons. If it's 1 electron, then you need to use that 4 divided by that volume. And that volume, this is a cube, and the one side, it says the distance between those 2 atoms is 0.36 nanometer. So you are going to divide by a cubic, right? Because the volume of that cell is a cubic. So you are going to have this okay, so then if you do the calculation, you will get the number for the electron density in the copper. And I will just show the results here. So it is 2.5 times 10 to power 22 centimeter cubic here. So here you will see that in the later part of the course, for the distance or for the length, typically we use centimeter, cm, in the semiconductor field. And then you need to convert all the units to the centimeter, cm. And centimeter, you know, is 10 to negative 2 meter. Okay. And then if you convert nanometer to centimeter, you have 10 to negative 7. So if you do the conversion. So I will leave this conversion to you, but if you do that, you get this. So that means within 1 centimeter cubes, this kind of volume, you have 8 times 10 to the power 22 electrons. So that is the density for the electron. Any questions?
How did you get 4? How did you get 4 atoms per unit cell?
We derived here, right? So for those polar ones, because 1 4 here, only 1/8 belongs to this cell. But you have 8 of them, so it's 1/8 times 8. And then for those in the center of the face, half of them belong to the cell. And then you have 6 of them. So it's like this, it's 1 plus 3, so you have 4. And 4 in this A cube volume. Okay, so then you see this density. It's pretty high density for the electron density here. And similarly, you can do that for the aluminum. Aluminum, the crystal structure may be different, and also the distance between atoms may be different. But you can use the same approach to do the aluminum. So this is for copper. Okay. And then you may consider the copper or aluminum for the interconnects. And which one do you prefer? So the criterion here is the resistivity. You want the interconnect to be lower resistivity. because you can transfer the signal faster and less power consumption. So you want lower resistivity. And the resistivity, if you have this kind of table, you want to fill out the resistivity. So if you go back to the previous derivation, we have that we have this equation. Sigma equals n q mu. Okay. If you then use that, sigma equals n q mu, and then 1 over rho is sigma. Then rho is 1 of n q mu. And then, for example, for copper, we just derived the n is this number, and the q, what is q? Q is the basic quantity of the charge, which is a constant. Physical constant is 1.6 times 10 to the power 19 coulomb in the SI unit. So this is a constant. And then the last is the mu. Mu is the mobility. Then you have this mobility. Here is for copper is 43. And then the unit is centimeters, so you are going to cancel that. And then eventually if you do that, you get the resistivity. I'll skip that. I think what you do here will give you, what is missing? I have to redo it. Something wrong with this system. Something wrong. So if you do that, I think you will get this number like 1.7. Oops. It's down again. Okay, anyway, so you do it, then you will get 1.7. And times 10 to the negative 16. And you can use that as micro. So eventually you can do this, and then you can get those two numbers for copper and aluminum. So you see that the copper has lower resistivity than aluminum. So that's why you prefer copper to be used for the interconnects. This is exactly true. You can also compare with other metal, like tungsten. And so tungsten is about 8, aluminum like 2.7 or 3, and then the copper is like 1.7. So it's lower resistivity than other metals. So that's why the semiconductor industry prefer to use copper. So in the old technology above like 130 nanometer, the interconnects are made of aluminum. But below 130 nanometer, that means after the year 2000, the industry switched from aluminum to copper, and today is a copper interconnect because of lower resistivity than aluminum. And actually, copper is the second lowest resistivity of the metal. So it's not the lowest. It's not number one. Can you guess which element is the lowest?
Gold.
Not gold.
Silver.
Silver, yeah. Silver has the lowest resistivity. But the industry didn't use silver. What? Can you guess why?
Expensive.
That's actually one valid reason. Yes, of course, silver is more expensive than copper. So that's a valid reason. And another reason is the diffusion of the silver into the silicon will kill your circuit, will kill the transistor, will have a short circuit problem. So actually for all those elements, you want to confine the copper only in this region, right? You want to confine the copper in this region. So this is an insulator in between. So actually you don't want the copper diffuse into those oxide. So you need some barrier actually here. You see actually in this image, you see there's a little bit lighter region. So that is the surface, the barrier to prevent the copper atom goes into the oxide. So and typically this barrier is this TAN, the tantalum nitride. So we can use copper because there is a very good barrier for as this tantalum nitride, but there's no good barrier for silver. Okay. So silver can very easily diffuse into this oxide. Then you may have short circuit between, let's say, two metal lines, or it may also go into your transistor, and then will make the transistor not working.
Is this like diffusion during production or like long term?
Long term, especially when you have higher temperature, then those atoms tend to move around, then you will have the short circuit problem. And we have the barrier for the copper, but we don't have a good barrier for the silver. Okay. This is another reason. And of course, silver is more expensive. Okay, any other questions? So I think for today's lecture, we are done with today's lecture, but if you want to look at what are the key points of today's lecture, so I think that derivation